All right, this is our topic 2 on earthquakes. So we're just going to go over all the things we need to know about earthquakes. This very first slide shows you, it's a video, but I can't show it to you. I'll post it on the Google Classroom. It's in Mexico City in September 2017. There was a 8.2 earthquake in that area, and it shows sort of the effects of what happened. So what are earthquakes? Well, they're a result of the activity of tectonic plates. When two plates push against one another, pressure builds up, and eventually this pressure is released and an earthquake occurs. The initial breaking point along a fault, the location where two plates meet, is referred to as the focus of an earthquake. Seismic waves transfer energy released at the focus through the surrounding crust to the epicenter that lies directly above. These waves can travel vast distances, explaining why earthquakes are often felt hundreds of miles from the epicenter. So basically, these waves or energy is transferred through waves far away from that focus point or that epicenter of an earthquake. So if we look at the world, who is the most at risk for having earthquakes? Well, the places that have like that darker red would be high hazard to very high hazard. So if we look all along in North America, all along the coastline, so up in Alaska, all the way down BC, down the west coast, all the way down through to California and then Mexico. So that would be all of that higher points or chances of getting. And then again, all the way down the total left side or west side of South America, you're going to see higher risk. So that's due to the tectonic plates that are there. And maybe some of you have seen that movie, San Andreas, with The Rock in it, but that is a very dramatized movie about an earthquake, and it's on the fault line. So San Andreas fault line runs along California, I think near San Francisco, and they tend to have pretty severe earthquakes around that area. If we look over, not a lot of earthquakes possible in Africa, but in Europe and into the Middle East and then into Asia, definitely lots of places that earthquakes are a possibility. So what are the types of seismic waves? After energy is released at the focus of an earthquake, it's transferred upward to the Earth's surface through two types of waves. The primary waves, or our P waves, these are the first to arrive at the surface as they travel the fastest. They're a low-frequency sound wave that can travel through solids, liquids, and gases. This travels through a series of compressions and expansions, causing minimal damage to rock. So these primary waves are the first waves to be released from the epicenter or that focus point of our earthquake. The secondary waves, these are the second to arrive at the surface as they travel slower. They are high-frequency waves that can only move through solid rock. These vibrate up and down as the waves move forward, transferring more energy and thus causing more damage than a P wave. So just to recap some of that, you guys might not know what some of these words mean, but a low frequency, a wave that's very low would be like this, like really spread out. If we go over here, a very high frequency wave would be something that would be like this. So the energy takes longer to get somewhere because it's going up and down like this compared to our primary waves, which are, I guess, faster because they're not releasing as much energy as they move along. So that makes them not as damaging. These secondary waves, or S waves, are going to be more damaging because as they move along, they're releasing a lot more energy. And that's They're transferring more energy and thus causing more damage than a P wave. This vibrates up and down, and the main thing here is that these high frequency waves can only go through solid rock. I'm not using the right, I wanted to show that. Anyway, solid rock, yeah. So that's the one that goes through solid rock. These ones can go through solid liquids and gases. All right. So surface waves, this is once energy from the focus reaches the Earth's surface, it travels across the crust through a series of surface waves. Surface waves move along the ground, much like a wave of water. So you see that in the picture. Like S waves, surface waves can also move the ground from side to side, causing a significant amount of damage. So those surface waves are going to be also pretty damaging on the surface of the Earth. Surface waves travel slower than S waves, so they're slower than our secondary waves, and thus do not travel far from the epicenter. So surface waves are pretty close to that focus point or that epicenter of the earthquake. So if we compare the three motions here, P waves, they're not very high up. They have very low frequency. S waves, really high frequency, so they have really high arches. And then our surface waves are more rolling motion and tend to not go quite as far. All right, so our S waves are the most damaging, and they're the strong shaking, where a P wave is more of a smaller jolt and light shaking. Because it can go through solid liquid gas, it's not really moving things quite as much. So seismology is the scientific study of earthquakes, and a seismograph is a device that can be used to track the size or amplitude of P and S waves, as well as the time interval between the arrivals of these waves. The time interval between the arrival of P and S waves is used to determine the epicenter of an earthquake. The time interval is also used to determine the magnitude of an earthquake on the Richter scale. So you may have heard of this before. The Richter scale is the scale that they use to measure earthquakes. And the closer together the waves, the higher the magnitude, or higher on the Richter scale they are. So the waves closer together, higher magnitude, because they're bringing more energy at a time, which means they're going to be more damaging. So this little graph here shows chart, I guess, shows the time interval between P and S waves in seconds, and then distance from the epicenter. So as the waves move, this is showing how far they're moving in kilometers away. So as the waves start to move at 1 second into the earthquake, they are only 9 kilometers away felt. And as time goes on, these P and S waves, 40 seconds after the original epicenter of the earthquake, they can be felt as far as 340 kilometers away. So locating the epicenter, it says the amount of time between the P and S waves of an earthquake can be used to find the distance to the epicenter of the earthquake. The minimum of 3 readings from the 3 different stations is required to accurately determine the epicenter. Based on the readings collected by the seismograph, the P and S waves occurred approximately 15 seconds apart. According to the table in the previous slide, 15 seconds is equivalent to about 128 kilometers from the source. Thus, we can conclude that Station A, where the seismograph is located, is approximately 128 from the epicenter of the earthquake. So basically, by looking at the waves, they can tell how far they are away from the epicenter, so wherever they're measuring these waves. A single reading does not give an accurate idea of where the epicenter might be located, and it could have occurred 128 kilometers in any direction from the station. So it's basically showing you 128-kilometer radius. So in any sort of direction. That's why they need to take multiple readings from different stations to determine or narrow down where the epicenter is. Okay, so if they're at station A, they might have another station here that's going to figure out how far away it is, and another station here, and so on. So all of those readings will go together to figure out where the epicenter is. Oh, it shows that right here. So if 2 or more readings are obtained from other stations, we can use these distances from the source to accurately determine the epicenter of the earthquake. The epicenter is located at the point where the 3 circles intersect. So we're seeing, we can draw these circles sort of on our graph or on our map to figure out where that epicenter is. So where they sort of overlap would be considered the epicenter. So how do we determine the magnitude of our earthquake? Well, the Richter scale uses the time interval between P and S waves, as well as the maximum amplitude of S waves measured by a seismograph to determine the magnitude of an earthquake. An example is that a seismograph measures the amplitude of S waves to be approximately 60 millimeters. If the station is determined to be a distance of 700 kilometers from the epicenter of the earthquake, then the earthquake must be a magnitude of 7.0 according to the Richter scale. So on this scale, they can, I guess, draw a line between the amplitude and the distance. See, amplitude here, distance from the epicenter, and then if they draw that line, that'll show you where on the graph on the Richter scale is the magnitude. The Richter scale is a base 10 logarithmic scale, and this means that every single point increases on the scale indicates an earthquake that is 10 times stronger than the previous point. An earthquake with a magnitude of 7, for example, is 10 times stronger than an earthquake with a magnitude of 6. And an earthquake magnitude of 8 is 100 times stronger than an earthquake with a magnitude of 6. Okay, so on the scale, it shows you sort of how these might be felt. A 0 is unfelt. 1 would be somebody felt something, a minor. Small is a movement that may or may not be routine, hard to say. Moderate is an event that earns something attention and is worth sharing. So as we go up the scale, that goes from 0 to permanent, which is an impact capable of causing global change and the future of civilization as we know it. Okay, that might be a bit dramatic, but yes, 10 would be definitely extreme. I'm not sure what the highest earthquake that we've ever had. I guess it's going to show you right here. So this is number of earthquakes per year worldwide. Showing the energy that's released, some of the earthquakes on the magnitude scale. So Chile in 1960 had an earthquake that was almost, I would say, 10, if I was able to draw a line here. That's not a straight line, but you get it. It's pretty close to that 10 mark. Alaska had one that was over 9 in 1964. So in the 60s, there were some pretty bad earthquakes. In San Francisco in 1906, there was a pretty major earthquake. You see some California ones there. There's one in New York and Long Island in 1884. But yeah, so this is the ones that were measured over time, and lots of damage, loss of life, definitely as you move past the 6 point. And this is earthquakes. Can they be predicted? Well, there's a video here. I will put it onto the Google Classroom so you can see it. So there is some questions that go along with topic 2 here, and you should have that in your package that you can complete for this week. All right, have a good day, and if you have any questions, please let me know.